all in this weird bag. And I pick one. So what's the probability I pick a red poker chip?
26.
Yeah, so it'll be 7 out of 26. Good. So if I give you this kind of problem on a quiz or a test, triple check your addition. It so sucks if I ask you like 8 questions and all your denominators are wrong because you didn't add correctly, right? So there are 26 total chips in there, right? For pretend. I don't have any poker chips. So it's 26 total. So every one of these is going to have 26 on the bottom because that's the total possible number of things that could happen. So out of 26, there are 7 that match what I'm looking for. Now, let me say the most common mistake I get, and see if you can tell where somebody comes up with this.
They pick one color. There's 7 chips. They said it was a 1 in 7 chance.
Yeah, there's 7 chips. I'm going to get one of them. Well, no. There's 26 chips, right? So this, I understand the reasoning behind this, but I really want you to make sure that you understand why this reasoning is not correct, right? It's like focusing totally on the red, and I want a specific red one, right? I want the red one, I don't know. So that's not right. So it's got to be the total on the bottom and the total that match what I'm looking for on the top. I got 7 chances out of 26 things. I like it. So what about this? What's probably you get what did I say? That was blue or green. So what does or seem to mean? Where'd you get 19 from?
Added up blue and green chips.
Yeah, because now our chances increase because now I'm saying I could get blue or green. I'll be happy either way. So the chances that I find something I'm looking for increases because what I'm looking for, there's more options. So or seems to mean, what did you do to these? Add them. All right. Or seems to mean add, possibly. Let's keep that on the side because we got to investigate that further. But or seems to mean add. I probably wouldn't say that if it wasn't true. But we'll see a little bit later. There's a little bit weirdness there. So or add, I don't know. Or equals add. Maybe. We'll investigate. You guys with me so far? Okay. What's the probability? I pick a blue and a red chip. Let me make sure you guys are okay with the English language and how it doesn't work well with math. So how many chips am I picking? No.
One.
So I'm picking 1 chip. So I want to pick the first probably I got a chip that's blue and red.
0.
0. You with me? So and in this case doesn't mean you and you come with me. It means I always call it the mean bouncer. You go to a club and they say you can't come in. You got to be rich, and you got to be good looking, and you got to have nice clothes, and you got to drive a nice car. And I'm like, you lost me at the first one, right? The nice bouncer would be you got to be rich, or see that's why or means add. It increases the chances you're going to do something, and decreases. How many people match all of those things? Very, very, very few people. And I'm like, they're probably all dorks anyway. I'm going to go somewhere else, right? And you must be a huge dork. Okay. Sorry. Yeah, he's like, is he speaking from personal experience? I'm going to let you figure that out. Let's see. Oh, so this will obviously be 0. Because there are none that are both blue and red. So be careful about the English meaning of and. In English, and means several different things. Math says, English, stop that shit. And means it must be both. That's what and means, all right? In math. Cool. I like it. Blah, 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 blah. Oh, they're already doing that. So let me show you. Oh, here's a little preview. We don't know enough math yet for this. But let's say I picked 2 poker chips. Pick 2 poker chips. So if I ask you so first off, if I pick 2, what's the sample space?
13.
Now how big is it? Or what? I'm sorry, what did you say? 30?
13.
13. No?
No.
Sample space, like for two kids, was boy, 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 girl. So you got
Oh, yeah.
red, red. Yeah. Red, red. Red, blue. Red, green. Blue, red. Blue, blue. Blue, green. Green, red. Green, blue. Green. All right, so again, why does it make sense that it came out to be 9 things? There were how many options for the first chip?
3.
And how many options for the second chip? 3 times 3? It's 9. Boom! It's my own personal magic. But now, let me see if you guys can get this. If I said what's probably a red, red, it is so not 1 out of 9. Are these equally likely? In fact, let me ask you like this. What's the most likely thing to happen in here?
Green, green.
Green, green. Why green, green? Why would that be most likely green, green? It's just fun saying green, green. Because it's got the most freaking chips. What's the least likely thing?
Red.
Red, red. Right? Red, red. No? No shiny? No? Okay. You guys have no idea what I'm talking about?
I do.
Red, red. Shiny? Thank you. I like you. I'm laughing on the inside. I don't care. All my jokes are for me anyway. So red, red. We don't know enough. All I can say is it's the lowest possibility of anything in there, isn't it? So lowest probability. But what is the actual answer? We don't freaking know yet. So that's why I want you to be really careful about. If they give you this and they say, what's the probability? You got to say to yourself, are they equally likely? If they're not, you're going to have to use some advanced method that we'll learn later. It's not that advanced, don't get crazy. How can I make them all equally likely?
Same number of chips.
Have them all have the same number of chips, exactly. Cool, I like it. And then it would be equally likely, right? Yes, sir.
When it comes to like picking, let's say, two poker chips in this case, let's say once you take out the first one.
All right, that's coming later.
Okay.
Right now, everything I said is true, and then there's a little bit. I can take the first chip and put it back in,
Yeah.
or I can take the first chip out and feed it to my little brother or something, and then that changes all the rest of the probabilities, right? So that's coming later when we investigate that a little further. Okay, so what I want to do now is I'm going to give a problem a lot like this on the quiz, but I'm also going to give a problem a lot like that was imaginary. A lot like this one here, and this is what's known as a contingency table. Well, that sounds nifty. But it'd be something like if you ask several men and women their opinion on something. Let's say yes, no, I don't freaking know. Right, so I ask you, and you can just make up your own question that was asked. I'm going to put the numbers up here. And let's say that 11 men said yes, 3 men said no, and 2 men said they don't freaking know. 6 women said yes, 21 women said no, and 5 women said they weren't sure. So this is also a really rich place to go for probability questions, right? What do you think? I'm going to start asking questions like, what's probably it's a woman? What's probably it's a man? Or they said no. I mean, I'm just going to put the first couple of questions down here. But what do you think I should start? What I should do even before I look at those freaking questions? I got to see what the totals are because probabilities are based on totals, right? So how many total people said yes?
17.
All right, this is the first place. I always have people that don't read these things correctly. For some reason they say, yes, it was this. No. That's what is this? Men. Right? Let's put this over here. There you go. So there were 17 people that said yes. How many people said no? 24. How many people said they don't know? 7. How many men were there? 16. And how many women were there? 32. Cool. And then, please, dear God, 48, right? And then you don't add these in. Why would that make no sense? Let me add these to these. What have you just done? You've just doubled everybody, right? It's neat. They're all clones. So 48, and a real quick check is this better add up to 48 also, right? Does it?
Yeah.
Yes, thank God. Okay, good. All right, let me stop there for a second, let you guys catch up. So I don't know if you picked up on this, but I enjoy this kind of problem. I like giving this kind of problem because I can ask every probability question on this setup. So yeah, that's why I like it. Right. So what I normally do is I use information you gave me in those surveys, and I construct it out of you guys. Sounded weird. Take you and I make it out of you. No. Sorry, smiling so lamsy. What is the probability if I picked one person? Be very specific, because I could pick several people from this, and that makes it really gross. If I picked one person, was probably that the person I picked was a woman. Yeah, 32 out of 48, which you can reduce. And give an eye roll. Come on now. Now watch this real quick. Let me show you a little trick. How far apart are these? 16. So if 16 might go into both, possibly, right? Because if two numbers are 4 apart, then if 4 goes into 1, it's got to go in the other one, right? It's multiples of 4. Does 16 go into both? Yes. Yeah, 2/3. Which is what is a percentage roughly? 66.7. I like it. Okay. So what about probability that the person I picked was a man, or they said no? Here's where people make another common mistake. So I want this person that I picked to be a man, or somebody who said no.
40.
Yeah. So if I say 16 men plus 24 said no, what have I done wrong? And everybody said 40. You're like, I don't know what you did wrong, man. That's what I said. But if I add these people to these people, I have added
double. No, you've added men.
What's the matter? Sorry.
Sorry, or no, sorry.
Yeah.
You've added men's no twice.
Yeah, exactly. I added these people twice. How did they get double the votes in something or whatever? Right? You with me? It's like saying, if you're a man, come in and vote. Okay, now if you're wearing brown shoes, come in and vote. Like, oh, okay. Every man with brown shoes just voted twice, right? Let's get going. Look, brown shoes, I'm ready. Sorry. So what should I do to adjust this? I have to minus 3. So now we actually can do it, actually. We can develop a formula for or now, believe it or not.
That's 48, right?
48, I don't know where 36 came from. Sorry. Where did 36 come from? I have no idea. So what's that? 37 out of 48, which is roughly what percentage? 75.7.
77%.
It's close. 77%? Okay. Is everybody cool with that problem there before I do this next thing? That's right, this is the room with no clock. What time is it? Somebody know?
11:40.
Yeah, this is your chance to say it was 12, whatever. But you lost it. So, let's take a little side note here. Let me actually remind us from earlier. When I had the, what was it, blue or red? Remember that? Why did we just add blue and red? I didn't have to subtract anything. Because how many chips were both blue and red? None of them were, right? So I always do what I'm about to say I do. In general, the probability of A or B is the probability of A plus the probability of B, but you got to subtract any that are both A and B. So minus the probability of A and B. Because those would be the ones that you counted twice. Now, when you have this situation, you don't have to do the formula. You could just be smart about how you count. You could say 16 men plus 21 people I haven't counted yet that said no. I mean, you see, don't count them in the first place. Does that make sense? You don't have to do what the formulas say because the formulas are the most general things in the world. In a specific situation, there could be a quicker way to do something. Hell yes. You probably have never heard a math person say that before, but that's the truth, right? What was I going to say? Oh, well, too bad. What about, so let me ask you this. On the heels of all that, this should be an easy question. What's probably that I picked somebody who's a man and they said no? What? What? Probably a man and they're a person that said no. And remember, I'm picking one person. Beautiful. Remember, and is the mean bouncer. Fewer and fewer and fewer people. So whenever there's an and in a probability statement, the answer is going to be smaller, most likely. At most, it'll be the same, but normally be smaller because there will be fewer and fewer things that are both. You're going to be a man, and you have to have said no. Only 3 men said no. Out of what? 40. Beautiful, because who could it be? Anybody still, right? So see, the beautiful thing about and, another name for and is intersection. So some of you guys, I don't know if you've ever seen this this symbol before. It was the intersection. The other one was for or. It's the or one is union, right? And I love that symbol. It's like you or you. I don't care. That's the symbol for or. You or you. And the other one, it looks like for and. Anyway, so you have to know those symbols now. Screw. So and is always going to be smaller. We still haven't figured out mathematically. If I didn't have all these numbers to count, what would I do mathematically for and? I don't know yet. We're going to figure that out later. All right, so one last type of problem, and then we're going to leave early. Let me see where I'm at. Okay. So still, just picking one person. What's the probability that I pick somebody who, that I pick a woman, given that they said no? Oh shit. So think about it. What's the only time the bottom can change?
What do you mean the bottom?
The denominator.
You have to include yes. It's like the only way right now is like if you're only thinking about if they said no, not if they said.
Exactly. I love it. If somehow you're eliminating possibilities, right? You with me? And isn't that exactly what this is saying? What do I know about this person? The probability that it's a woman, given that they said no. So what do I know about this person? They said no, because it says the probability is a woman. Do I know they're a woman? No, that's the point of the question. What's the probability they're a woman? Given that they said no. So what's going to go on the bottom then?
4.
Why? Because that's how many people it could be. I love it. See, the bottom is always the total number of things it could be. And what's the only time it's not going to be everything? When you get given information. I love it. So now this is going to be out of these people. So your whole universe is those people. Out of those people, how many are women? 21. Kick ass. Right. 87.5%. Yeah. Cool. Maybe. So what's the formula for this? A general formula. Where'd the 21 come from?
Total number of men.
No, the total number of women is 32.
Total number of men.
Where'd the 21 come from? They had to be women that also said no. So the women and no. You with me? Because why does that make sense? Given they said no, so the only way that a woman could have happened, that's a weird phrase, but oh well, the only way a woman could have happened is if they were a woman who said no, right? So on the top is going to go the probability of A and B. And what goes on the bottom is the probability of B. So given B, so I know B, something in B happened. So that's got to go on the bottom. What's probably A also happened? Well, then A has to be a part of B in order for it to possibly happen. Right? And visually, I don't know if you guys have ever seen Venn diagrams before. If I tell you B happened, what's the only way that A could have happened? Is if it's in here, right?
Yeah.
And what is this? That's A and B. So it's A and B divided by B. That would be the probability of A given that B happened. I like it. All right. That's plenty. We've done a lot today. Holy shit. I don't know if you realize it. You probably, maybe it doesn't feel like it. I don't know.
What section?
I don't know. 3.1 is sort of an overview. We did a little bit of we did a little bit of a lot here, actually, because 3.4 is all about contingency tables. So we basically just did 3.4, bam. We did all of 3.1 for sure. We did a little bit of 3.3. So in your homework, you'll at least do 3.1. You can all do 3.1. And that's plenty, so that's it. You're all free to go.